Welcome, this is Dr. Plague. In my last video, I worked on building the hardware for a flash memory programmer. In this video, I'm going to continue on with that project. Now, in order to use this programmer that I made, I'll need some type of serial UART to USB cable, like this one. This is the FTDI TTL-232R-3V3 cable, which is 5-volt tolerant. If you make one of these programmers, then you need to make sure yours has the correct pinout on the connector for the cable you're using. In my case, this connector has ground on this pin, followed by CTS, VCC, transmit, receive, and RTS. And I'm only using the VCC, ground, transmit, and receive pins. When the cable is plugged into the computer, you can access it in TeraTerm, and it shows up as a USB serial port. Of course, we'll need to apply power to the programmer before we can communicate with it. And before we communicate with it, we need to develop the firmware. Now, before I continue, I want to address something that I forgot to mention in the last video. Why am I using external power for this programmer? Why not just power it through the USB connection? You see, I'm not connecting directly to the USB bus, but rather connecting through the FTDI serial to USB cable. The particular cable that I am using is rated for low current, and it only pulls 1 unit load from the USB port. This current needs to power both the FTDI cable and any loads connected to it. This one only provides a maximum of 75 milliamps, and we can only draw 2.5 milliamps during a suspend period. I don't want to lose power in the middle of a write if the USB port is suspended, so I'm just using external power to be safe. And while the programmer is low current, this does not mean it won't draw more current in the future, depending on which chips are being programmed, or whether external circuitry is added through an adapter board for high voltage programming, etc. Now, the ultimate goal is to create a computer app for programming chips like I showed in the last video. But I'd also like to use the programmer without that app. If I have just a few bytes that I want to program into a flash chip, I don't want to have to make a file to send to the programmer via an app. I want to be able to connect to the programmer using some type of terminal program, such as TeraTerm, and send it my own commands to program a byte here and there. The firmware that I will start developing in this video will also allow an app to connect to it for programming large files if desired. We'll look at how I developed that app in a future video. Now, let's get started with developing the firmware. For this, I'm going to use one of these Atmel ICE programmers. I'll just connect it to the programming port on the board, and I'll connect it into the USB port on my computer through this hub. I'll also connect the FTDI cable to the board and a USB port. I'll make sure I provide external power to this board, and I'll set that voltage to 9 volts. Now we're all set to start coding this thing. I'm using Atmel Studio 6.2 for development. It's free, although I believe the latest version is now called Microchip Studio. In any case, you can use whatever development environment that works for you. I'm not going to show how I started the new project, since I made a past video on that. The link will be in the description. You can see that I pulled in some additional files to this project. I have the UART files with the init file, which I created in a past video on using printf and scanf with a UART on AVRs. Again, the link will be in the description. I also pulled in the circular buffer files, which are used by the UART files. See the link in the description. And then I have this here bits header file, which just contains a few defines to set, clear, and get the value of a single bit in a byte. Now, if we go to the main file, you can see that I've added a detailed comment section, which lists the expected pinout of the microcontroller. I like doing this for all my projects. It just helps with the coding, so I have something to refer to on pin usage. So, for example, if we look at pins 1 through 8, they are set as an output, and they are connected to address lines 0 through 7 on the memory chip. This corresponds to what I had drawn up in the schematic that you saw in the previous video. And all the other pins are described in this comment section. So first, I'm going to add in a startup delay. This will help give time for any bouncing of the reset switch. And for the delay function to work, I need to add in the proper header file. And I'll also need the init file to define the CPU frequency for proper delays. Let's include the UART header file and declare the UART stream here. Then I'll start the UART with a baud rate of 115.2. Now I'm going to clear the screen and move the cursor to the home position. I'll do this with some VT100 escape codes, since Teraterm accepts them. I'll define the escape code and add that into the printf function. I need to include the standard I/O header file for printf. Then I'll display some version info. I'll just call this version 1.0. And I'll indicate the programmer is ready. Next, I'll print out a prompt, and I'll choose the greater than sign. You could customize yours however you'd like. I want the user to be able to enter single character commands. So I'll create a variable to hold a command character. And let's get a command from the user. Notice that I placed a space before the %C. This will help eat any white space before the command is entered. Then I'll process the commands with a switch statement. And for now, I'll just add in a default case for an unrecognized command, and show the user which command was unrecognized. Okay, let's compile this and see if we have any errors. And it compiled fine, so let's program it into the microcontroller to test it out. So let's set up Teraterm and reset the programmer. You can see that it displayed the version info, ready, and the prompt. And if we try entering some commands, they're all unrecognized for now. And by resetting the programmer, we can see that the clear screen functionality works just fine. So, we're off to a good start. Let's continue. I want to include a command that displays a list of commands, in other words, a help command. I'll just use a question mark for this. Next, I need to create the help function, or else the compiler will bark at me, or maybe it'll just give out a little growl. For this, I'm going to create some new files so I have a place to put the new command functions. I'll create a C file named commands and create a matching header file. I want to include the commands header file to the main file and also to the commands C file. And here's the new empty help function. And I'll just place the prototype into the header file. I like to include the AVR I/O header file to all the header files, so I'm never missing anything AVR related. Okay, let's go back to the help function and print the command list. So far, we only have one command, and that's the help command. And I need the standard I/O header file for the printf. Let's get this compiled and programmed to make sure it works. And this all works fine. Okay, let's go into the init file, include the AVR I/O header file that I like so much, and start defining the GPIO pin functions. I'll start with the data lines D0 through D7. And they're connected to port C. These are AVR-specific port registers. Now I'll copy those and change them to the first 8 address lines on port B. I'll name the first group of address lines Address 0. And the second group, A8 through A15, named Address 1, are located on port A. The third group, Address 2, will only consist of 3 address lines, A16 through A18. They reside in the high nibble of port D. Therefore, I'll add a mask to define the 3 bits. I want to define the 3 control lines starting with chip enable. And the control lines will be on port D. The 2 least significant bits of port D will be for the UART receive and transmit, and the most significant bit will be for chip enable, bit 7. Bit 3 will be the output enable. And finally, bit 2 will be the write enable. And I'll just line all these up. Now I want to create and add a new init C file to the project. I'll just include its own header file along with the bits header file. Then I'll create a new init IO function where we can initialize all the GPIO lines. And let's just put the function prototype in the header file. First, I'll set the write enable high, so we disable writes to the flash memory chip. And the first thing I'll do for this is to set the port pin to a 1, which will enable the pull-up, and this will just keep the write enable line high. If I set the data direction first, then it will output a low before I change that to a high, since a 0 is the default register value. And then I'll change that GPIO pin to an output. I'll do the same thing to the output enable pin. so the flash chip will not output a value on its data lines. I'm creating a programmer, so I want the flash chip's data lines to default to inputs. Next, I'll set the chip enable pin low, just to keep the flash chip enabled the entire time. If you want, you could keep it disabled until you access it, but I'll just keep it enabled. I want to set the data lines coming from the microcontroller as outputs. They're inputs to the flash chip, but outputs from the microcontroller. And I'll set all the address lines from the microcontroller to outputs. After all, the flash chip will never output anything on its address lines, so we should be safe doing this. I'll use the mask to set just the 3 most significant address bits. Then I'll add the I/O initialization function to the main function. I want to change all command characters to uppercase to help simplify the cases in the switch statement. And for that, I'll need to include the C-type header file. Let's add a function to read a byte, and I'll appropriately call it R for read. And I'll create the read byte function in the commands file and place its prototype in the header file. Now, I want to print a 2-character hexadecimal value to represent a byte that is read from the flash chip. And I'll just print the value of FF for now, just for testing the command. We'll program that in. And if we try entering the read byte command, we get FF as expected. Let's create some new files for low-level flash functions, a C file and a header file. I'll call them flash. Again, I'll include my trusty AVR.io header file and include the flash header file in the C file. I'm going to type define a structure named flash IC to contain identifying information about the flash chip. The information I want to include is the manufacturer ID number, the device ID number, and the memory size, and the current address location that we are dealing with. If you can think of anything else you want to add to that, then go ahead. Now, I'll create and initialize a global variable named flash. I'll give it an initial manufacturer and device ID of both FF. And set the size to the smallest flash IC size that we'll be programming, which is 128K. And set the address to 0. And I'll make this an external variable, so we can access it from other files. Now, let's create a function to read a value from the flash chip, and put the prototype in the header file. Let's include the flash header file in the commands file. And I'll change the static FF value to the read flash function and pass it the address that we want to read, and post increment to the next address for the next read. And notice that I'm using the flash variable to get the address. The first thing I want to do before reading a flash value is to set the address, so I'll create a function for that. And place the prototype in its local file, since it will only be used in low-level functions. I'll set address 0 to the least significant byte of the address. And mask it to a byte size, FF. I'll set address 1 to the second least significant byte of the address by shifting it to the right by 8, and mask it. Then I want to keep all the bits for address 2 except for the masked bits. I'll clear those, and I'll add the address shifted by 12 to put the next 3 address bits into the high nibble of the port using the mask. Now, we can get rid of these FFs since the ports are only 8 bits anyway. And I need to include the init header file to use the address line defines. I want to test this out on a scope, so I'll set all the address lines high, then set them low, so we can trigger off the address lines. It compiled fine, but the read flash function is missing its return value for now. And I'll program this into the Flash programmer. Let's connect the logic probe to the Regal scope. Now, we set the address lines in 3 separate lines of code, one for the group of A0 through A7, one for A8 through A15, and the last one for A16 through A18. So I want to connect one logic probe to one pin within each group of address lines. I'll connect probe D0 to A0, D1 to A8, and D2 to A16, and connect a ground probe. Now I'll issue a read command to toggle all the address lines high and back low. Look at that. It took about 250 nanoseconds between the first 2 groups of address lines, but it took about 5 microseconds to get them all set. What's going on? This is not very optimized if you ask me. Let's go into the debug folder and take a look at the LSS file. This will show us the assembly code that the compiler generated. Let's find the set address code. Wow, look at all that code just to set the address lines. And there is even some looping going on in here. This is horrible code. Let's see if we can improve ourselves. First of all, I want to type define a union between a 32-bit value and an array of 4 8-bit values. Now we can directly place the 32-bit address into that union and individually access the 8-bit byte values without needing to shift anything. We'll put the first or least significant byte into address 0 and the second byte into address 1. And we'll only need to shift the next byte left into the upper nibble. Let's give this a go and see if the generated code is any shorter. And look at that! There are now no instructions between the first two outs, and a lot less between the second two outs. Compare this to the previous code. Let's program this and see how it performs on the scope. Wow, look at how much better that is. Now we can zoom in a little more. We have only 50 nanoseconds between the first two here, which accounts for the AVR running at 20 megahertz. But we have about 550 nanoseconds between the last two. You know, if we look back at the code, there's a lot of stuff between the last two outs. But we only really need to swap the nibbles, since the upper 5 bits of a 24-bit address should always be 0. Let's see if we can trick the compiler into using the assembly language instruction named swap. That instruction swaps nibbles. To do that, I'll just add the same address byte to itself. One shifted to the left by 1 nibble, and one shifted to the right by 1 nibble. Let's take a look at the code now. And we have the swap instruction right there. Look at how short this is now. Let's program it and look at the scope. And now we only have 300 nanoseconds between the last two. Another improvement of shaving off 250 nanoseconds. The total time for all the address lines to set is now only 350 nanoseconds, plus a little overhead for the function call. But compare that to 5 microseconds. It used to take more than 14 times longer. That was a worthwhile optimization in my book. You can always look for more opportunities for further optimizations when you write your code. Okay, let's continue on. Now I'll get rid of this set address instruction and just keep this one, but I'll have it set the address. Then I'll have this function return the data from the data pins. But before we can do that, remember that the flash chip has its data pins set to inputs because the output enable line is pulled high. So we need to pull the output enable line low before reading the data. And we should set it back high after reading the data. Since I'm adding code after the return, I need to first store that value, then place the return at the end of the function. So I'll create a data variable to accomplish that. Now, let's write the function to enable the output from the flash chip. And I'll just put the function prototype right here. Now, before we enable the flash chip's output, we need to change the microcontroller's data pins to inputs to avoid bus contention. Then I'll just pull the output enable low. I need to include the bits header file to use the clear bit define. And I'll add the function call here. Now I'll create the function to disable the output from the flash. and put the prototype up here. And I'll first pull the output enable line high. Then I'll set the data lines back to outputs. You really don't need to set them to 0. It's just my OCD. And then I'll put the function call here. Let's add this command to the help printout. Let's give this a whirl. Now, remember back to my demonstration of the programming app in which I added data to the entire flash chip? Remember when I checked if it was blank and it found the value of 7F at address 0? Well, I haven't changed that flash chip yet, so we should still see 7F at address 0. And we do. Let's take a quick look at the file I programmed into the flash chip. This is my own hex file format, and the SA just means that the following data will be programmed starting from location 0. Then we have 7F, BF, and DF as the first 3 bytes in the flash chip. Let's continue reading bytes from the flash chip to see if this is correct. Well, that looks good. So we are reading correctly. But wouldn't it be nice to check which address we're reading from? Let's create a command for that. I'll name the command C to display the current address. By the way, I forgot to add a comment to the read byte command. Okay, let's just call a getCurrentAddress function. And let's create that function along with its prototype. And I'll just have this print out a 5-character hexadecimal value for the address. And let's put that in the help printout. Now let's give this a test. And we can see the addresses 0, 1, 2, 3, 5 after reading 2 bytes, so that seems to work. You know, it would be really handy if we could also set the address to any value we choose, so we don't need to keep reading until we get to the address we want. So let's add a command to do that. I'll just name this command A for address, but you could choose S for set address if you want, or whatever. So now I need to create the set current address function. Then of course add the prototype. And I'll just scan in a hexadecimal value from the user and put that into a param variable. And I want to make sure the function call was successful. If not, I'll print out an error message telling the user that there is a missing address. I'll put the param into the address variable and make sure it isn't larger than the flash size, which, by the way, we still need to determine. And for good measure, I'll just print out the current address after setting it, so the user knows if it got set correctly. And we'll add this command to the help printout. Let's give this a try. I'll try setting the address to 2, and that worked. If I read a value at address 2, I get DF, and the address got incremented to 3. And a couple more tests, and we're all good. I just want to make sure if by chance the address is set to something larger than the flash size, it'll get set back to 0. You know, I should have got rid of the ampersand flash size -1. Oh well, this is just a safeguard, so no big deal. I'll just copy this and place it after the main switch to make sure we don't increment the address past the end of the flash memory. And of course, I need to include the flash header file for that to work. And I'll make sure this compiles. And we're good. I don't know about you, but I'm getting hungry, so I'm going to call it quits for this video, and we'll pick up where we left off in part 3. We still have a lot of functionality to add in. We need to be able to identify the flash chip, we need to write data to it, we need to be able to erase it, and all kinds of stuff. So stay tuned for part 3. Thanks for watching, and I'll see you next time, right here on Dr. Play.